Welcome back to Physics with Miyoshi. Today we're here to talk about ideal gas law and a little bit about what that means. What is an ideal gas? First of all, it's a low density gas or low density gases. That means that the molecules are far apart that the molecules as they hit other things, they interact, but they not really tightly. So most gases tend to follow the ideal gas law, so we'll think about most of them that way. We also need to learn a little bit about absolute temperature. If you haven't known about those before, the absolute temperature scale is also called the Kelvin scale, and absolute zero is essentially when all matter would cease to move. The molecules in the matter wouldn't move anymore, and absolute zero happens to be negative 273 degrees Celsius, or another way to say that is 0 degrees Celsius is 273 Kelvin. The units are essentially the same as in our Celsius scale. So for every degree Celsius that you move up a Kelvin as well. So that's what Kelvin is, the absolute temperature scale is. There's also something you should know about something called standard temperature and pressure, or STP. Not the additive for your car, but standard temperature and pressure is 0 degrees Celsius or 273 Kelvin, and it's 1 atmosphere or 1 times 10 to the 5th pascals. That is what's known as standard temperature and pressure. As scientists kind of messed around with gases, they found a couple different laws, and there's a thing called Boyle's law, which states that the pressure and the volume, if I keep a constant temperature on a gas and I keep a constant number of molecules in there, then the pressure at any point in time will be pressure times volume will be the pressure times volume. If I increase the pressure, then the volume's got to change with respect to each other. There's also something called Charles' law. And Charles' law says that if I have a constant pressure and a constant number of molecules, then my volume and temperature will be related so that they're inversely proportional. As my volume goes, as my volume goes up, my temperature must also go up. So they're related that way. And then they all came back to one big law, which was that the ideal gas law. And the ideal gas law says the pressure times the volume, or the work done, is nRT, n being the number of moles. R is our universal gas constant, which is 8.31 joules per mole Kelvin, and then T for our temperature in Kelvin. You can also change this to be, instead of number of moles, if you want to know the number, if you know the number of molecules already, then you do PV is NKT, where K is Boltzmann's constant, which is 1.38 times 10 to the negative 23rd joules per Kelvin. Well, how do we use all this? What does it matter? Well, the reason it matters is because if we have, well, there's lots of reasons why, but if we have a volume of gas over here, and I make sure that the volume stays constant by not letting this piston go up and down, and I know the number of molecules will stay constant, so my volume and my number of molecules will stay constant. How do the pressure and the temperature relate to each other? Well, if we rearrange this equation, PV is nRT, then we can see that P over T must be equal to nR over V. Well, since I know that my N is constant and my V is constant, then I know that the P over T must be a constant. So if I change the temperature by raising the temperature or lowering the temperature, it doesn't really matter, then I know that I must have some relationship going on. And we can see that if I have this P over T as a constant, I can rearrange it so it looks like P is a constant times T, which hopefully you recognize is a straight line going through the origin. So if I had something like this, it could be a very simple line. My pressure and my temperature are related in such a way, since the number of molecules doesn't change and the volume doesn't change, then this must be a straight line relationship. Now it's a little bit not quite as nice, but it's still true that if I have now if I let the volume change and I keep my temperature constant, the pressure can change and the volume can change, then I have a different relationship. I can look over here at Boyle's law, and as long as I change the pressure and volume in such a way that I don't increase the temperature, then I can get a nice relationship. And that would be that would look something like this. And it actually, you know, it go all the way up and there, it's 2. And this is what's called an isotherm. Iso meaning 1, therm meaning temperature. And if we think about this, we can change the temperature anyway. We would have a bunch of these isotherms. We could have as many as we wanted, but they would be never touch each other, and they would be a little bit different depending on the temperature. So each of these guys would be a separate temperature where the pressure and the volume could change, but they change a little bit differently based on that the temperature that they are. So a couple applications, a couple of different fairly simple examples of the ideal gas law. Again, the ideal gas law can break up into Boyle's law. P1 V1 is P2 V2, or PV is a constant. Same thing with Charles' law, where it's V1 over T1 is V2 over T2, or V1 over T1 is a constant. And again, the ideal gas law. PV is nRT. Pressure times the volume is my number of moles times my universal gas constant times my temperature in Kelvin. Or pressure times my volume is the number of molecules times Boltzmann's constant times the temperature, again in Kelvin. So, ideal gas law, a little bit about how we use it, and a couple examples for you. So, thanks for tuning in for Physics with Miyoshi. Hope you tune in again for more. Thanks again.